Hi there. Thanks for joining. This is a presentation that will be focusing on cloud formation, Chapter 5, for dual credit meteorology at Floyd Central High School. And our goal here is to step through content that will be focusing on two major concepts. Cloud formation, which is a function of atmospheric moisture. We need to refine what cloud information we need to know for our upcoming exam. We'll set the parameters there. And then we'll move into a little bit of the communication that deals with atmospheric change from a human perspective, except it's intentional change. So let's dive right in. Cloud formation is because of a condensation nuclei event. So what we're looking at is an aggregate of small water droplets. And I want to really illustrate on that because we do not have a good understanding of how small these types of things are. So what we need for this to take place is condensation aloft. Remember, condensation is the change of energy from a higher state of energy to a lower state of energy. More formally, it is the reduction of kinetic energy of water vapor. So it settles out and it's got to set on something. And what it sets on is something called a condensation nuclei. We go into just a little bit of connection to chemistry here early in this discussion, and it's got to deal with absorbing or repelling water vapor. Adiabatic cooling, remember that? That's that change in temperature that we focused on. We did this early in Chapter 1. We said there was an environmental lapse rate of about 6.5 degrees that took place per kilometer as the air rose, and as that changed, it changed the temperature up into a certain point. So remember, that's what is at the core of changing a lot of the temperature. That allows the kinetic energy to slow down of moisture. And then with the presence of condensation nuclei, we can have settling of that water and we have a cloud. And that's why a lot of times our clouds are flat based, almost like they're on a tabletop that's invisible in the atmosphere, particularly those of cumulus in nature. The air becomes saturated and there's got to be a surface. That's the condensation nuclei. The condensation nuclei are what the water condenses upon. And we have two types of condensation nuclei that we'll talk about, but it deals with those most significantly that cause cloud growth. Hygroscopic are the condensation nuclei style. That's the type of molecule that absorbs water. They seek it. So hopefully you can remember from chemistry, we had hygroscopic and hygrophobic materials that either repelled or attracted water. And whenever they attracted water, we could have something as simple as salt be an example of that. And that's why a lot of times on a July day in the summer season or a particularly humid fall day, we're going to have potato chips or something with a lot of salt on them become soggy quickly because of that water-seeking capacity. And that's part of the reason why we see that. We also would see certain component failure on vehicles in parts of the world, or specifically parts of the country, where we would have salt spray keep more than normal amounts of salt molecules in the atmosphere. So it's no surprise that whenever you have vehicles that are next to a coast, even though they're not driving through salt water, they might have a more challenging time keeping the salt from causing corrosion on some exposed parts. But we've got a lot better with our manufacturing techniques than in the past. Growth is rapid and then it slows down as the water vapor is consumed, and we'll look at what it is that consumes that water vapor. The water vapor is typically spent on the production of precipitation. Let's get into our cloud classification. Two primary things that allow clouds to be classified: the form and height. Form, cirrus, cumulus, and stratus. You've heard of these before. Cirrus are those that are high, white, thin clouds. They can produce a halo of the sun or a halo of the moon. They produce some pretty neat things in regards to a disc-like appearance of those day or night sky objects. And then we have a cumulus cloud, which we're all familiar with. Those are the cotton ball types, the bunny tails, the ones that we imagine to be different shape and form. Stratus clouds are the ones we're the closest to. They're in the lowest atmosphere, and those are the ones associated with the days that are just cloudy all day. A lot of times it produces rain, especially in the Ohio Valley, and it's not necessarily an overly aggressive rain event. It just produces a nice, steady, misty rain. So the football game's not going to be canceled. We're still going to go run if we're in cross country or track. The baseball, softball, all that's going to go. The soccer event's going to take place. It's just that everything's going to get misted upon, causing us to have a sloppy environment. Not a flash flood or anything like that, just a drizzle on and off. And that's where we have that type of a stratus event. Height, these are the three heights that I need you to focus on. We have high clouds above 6,000 meters, 2 to 6,000 meters for mid clouds, low clouds are less than 2,000. And if the cloud gets low enough where it makes contact with surface, then we're going to change its name to fog. And we will focus on 4 fog types in this course. So let's get into a diagrammatic sequence here. Work on committing this to memory. So if you receive one of these on an assessment or something similar to them with blanks, you can do 2 things. One, add the correct name for cloud, like you see labeled in front of you, and make sure you can talk fluently about their altitude. You can do meters or you can do feet. It's up to you. Meters will give you a little longer durability. Feet is pretty good, but once you get to college, you're going to have to be more fluent with that in meters. Here's what we need to focus on, putting everything together. We have high, mid, and low clouds. High clouds above 6,000 feet, or excuse me, above 6,000 meters, about 20,000 plus feet. So high clouds could be present whenever you have that cruising altitude of a Boeing level jet and they're up there around 30,000 feet. You're going to have those clouds that some of you could look out and see the aircraft traveling through. The cloud types that occupy this part of the atmosphere would be cirrus, cirrostratus, and cirrocumulus. They are in order based on their altitudes, and they can exist and overlap a little bit. Do work on your characteristics. It's difficult to classify clouds without a little bit of characteristic background. So your goal should be to talk fluently or communicate fluently through a diagram or on paper about how the characteristics of clouds are different, what their names are, and where they're at as far as altitude in the atmosphere. Mid clouds, you can see those listed there. White to gray, stratified, veil, those types of things are typically used. You can see how words such as bright spot are those that are typically referred to as altostratus. Stratus, nimbostratus are all relating to the low clouds. And then we have a unique group that are vertically developing clouds, and that's your cumulus and cumulonimbus, because they can occupy several of the similar, or they can occupy multiple levels within these height categories. So a composite view in generic of what we need to make sure we understand for our next assessment is high clouds, low clouds, mid, and vertically developing. These are your 4 major categories of heights. And remember, you're at high clouds are about 6,000 meters. Low clouds are below 2,000 meters. Mid clouds are between 2,000 and 6,000 meters. Varieties of clouds. These are unusual things that can occur with clouds. We can have clouds that provide unique characteristics, and there's several images in your textbook that this presentation won't focus on. Some of you have even seen some of these in the sky. For example, the mantis cloud. Those are typically noticed multiple times a year, mostly in the fall or spring. And when we have a lowering or slightly lower sun angle, we can get a wonderful appearance of a sunset after a storm has moved through. And those are typically because of cold, dense, down flowing air within a cloud that has got a pretty high top to it. And those are things where we can have some type of a storm nearby. So a lot of times they're associated with cumulonimbus. Some people are a little bit concerned that they could be tornadic in nature. That's not their intention. It's just a downburst of air. And if you're underneath a cloud or in that region, you're on a golf course or something, you can certainly feel that. Most people will probably not be out during this type of a cloud production because it's close enough to storms to be aware of your environment. Lenticular clouds, surprisingly, these are reported as UFOs each year, and mainly because of their shapes that they appear to be UFOs in the atmosphere. And each year, people out west and other parts of the country will call these in to NASA or other governmental entities and question about UFOs. So it might be interesting to take a look at those or Google them. There's several great examples in your textbook. You've got a cloud chart that's a fold out in the back of your book. Might be neat to take a look at these. But these are cloud varieties that are a bit odd. And and they tell us a type of activity that is not necessarily traditional or regular. Fog is our next topic up. We have 4 fog types that we need to make sure we understand. There's a lot of intuition that goes into this, so not a very long conversation here. Radiation, advection, upslope, and evaporative. Fog is a function of dew point. When we can have fog near the ground, what we have is a dew point being met right at the surface. Biggest problem with fog is whenever, probably the most challenging situation with fog is freezing fog, especially for us in this region. We have a dew point that is close to a freezing temp or below the freezing temp. The dew point's right at it, and then we have material on the ground that is below freezing, and what we have is a glazing that takes place, and it can be very, very pesky because unfortunately with this event, our coldest temperatures are right at sunrise, and we can have people traveling to work at dark, and right as that sun comes up, it could be in the middle of the rush hour, it could be an hour before, or whatever the case may be, depending on the season, the exact time of day, and the amount of exposure of sunlight, then it can produce a treacherous situation. So there has been times that we have shut down bridges across the Ohio River. Overpass has been shut down, and they're waiting for a salt truck to come in because the fog freezes on impact. This year that this recording is taking place, there has been multiple accidents regionally because of freezing fog. We've had the 3-day event where we've experienced unusually cold temperatures that's depressed the temperature of the ground where it's below freezing. The surfaces right at the ground are below freezing, and the materials that are around your 2 or 3 feet are very, very cold. And we had a fog that was being produced as we had dew point being met, very still air, and we had several slide offs of our local roadways. So we do see those. Radiation, advection, those are 2 things that are somewhat related, where we have radiation in one particular spot, and that's where the energy is lost, and we can have dew point being met. Advection could be where we have an air mass moved over. So this, remember, advection is the horizontal distribution of air or horizontal motion of air. So where we have an area of intense radiation, we might have air move over it that is cooler in nature, and then we have fog that's often referred to as rolling in. And that's where we see these types of processes in certain pockets of our nation. Upslopes, very intuitive there. Think mountainous region. In the region of Floyd County, we do see some minor development here. Some of you have driven in local roadways, Mosier Knob, might be going up and down certain types of other knobs where we do experience this. Certain parts of Old Vincent's Road has enough quick change in elevation during a fog or a nimbostratus day where you're going to drive through that pocket of moisture, and that's quite unique for our region. Evaporative is as it sounds. This is the evaporation of material, which would take place typically over your agricultural body of water or a larger process, and we can see that a lot of times in our fall season whenever the air temperature is getting cooler but the body of water is still warm. So read through these. These are reinforcement of what's in your textbook. Not a great deal of technicality here, but these are things that you can spend a little time reinforcing your understanding of. But these are the 4 major fogs that you need to make sure you show proficiency on in the course. Here's a little bit of detail. This is where we get confused in society. We don't understand how small is. Look at the typical raindrop, about 2 millimeters. Compared to your hair, the raindrop is massive. However, when we look at condensation nuclei, the things that water vapor in the atmosphere, specifically cloud droplets, must land upon and build around, they are raindrops are huge. So there are millions and billions of rain droplets that are within clouds. However, there are millions and billions of cloud droplets in rain droplets. So when a rain droplet splashes down, that's at the expense of billions of cloud droplets. And this is why forecasting can be so challenging with certain types of precipitation. Whenever we have a short burst of rain, the cloud uses so much of its moisture that its energy changes quickly, and it can change the entire characteristic of the storm. So a lot of times it's frustrating whenever we miss forecast, but whenever we have unusually or unexpected bursts of precipitation, it can really dissipate a massive amount of energy. There are two ways in this course that we will focus on the reason behind precipitation. We have cold cloud precipitation and warm cloud precipitation. Cold cloud precipitation is referred to as Bergeron process, and that's what you see in this slide. So the Bergeron process is talking about the development of ice crystals at the expense of cloud droplets. So notice how cloud droplets are getting smaller. Cloud droplets are getting smaller because this is moving into the snow crystal. So snow crystals get larger and the cloud droplets get smaller. So imagine the situation here. A forecaster calls for 4 inches of snow, and it should start snowing at 4 p.m. or 3 p.m. So school districts let out early. But around 2 p.m., we have an unusual burst of snow, and it dissipates aggressively between 2 p.m. and 3 p.m. And it's not in the school corporation's district yet because it's an hour early. Say it's to the west of it. Then the storm has lost so much of these cloud droplets that were in the atmosphere. The school district that released early may not receive the snow on time, may not receive nearly that volume of snow. And the reason why is it can produce such a massive drop of precipitation. So the Bergeron process is quite unique. Some of the other characteristics that make this unique is we can bring language into like supercooling or supersaturated. And that's because of the unique characteristics that take place in the upper atmosphere. And just keep in mind when we say supersaturated, even though it does sound like it might be over 100%, it is over 100%. It's a minuscule amount over 100%. And the cloud is so saturated, it needs an area. These droplets, this vapor needs an area to land. But the crystals present are so few and far in between. Notice you only have one present there. As soon as there's one there, it's an immediate burst, and it takes place within a very pristine environment, and that makes it makes winter precipitation a pretty tough forecasting job. Collision coalescence. This is our warm cloud situation. This is one that takes place when the entire column of atmosphere stays warm and we don't have any moisture that is frozen to work with. So this is fairly intuitive. We have somewhat of a snowball effect. So think of building a snowman, and you have wonderfully wet snow that sticks extremely well together, and you're wanting to build that lower tier of the snowman. You're going to take a snowball and begin to roll it up, and as it rolls up, you have this large base of the snowman. You can't pick it up, it's too big, but it sticks together very well. And that is similar to what takes place with the collision coalescence, except it's not snow, it's water. We have a small water drop in the upper atmosphere. It begins to fall, and as it falls through smaller cloud droplets, the cloud droplets collect, they coalesce, and as they coalesce, it makes the water droplet bigger. Eventually, the water droplet forms into a raindrop, and it can be so big that it shrapnels apart into different components, and it creates a shower. So what we see here is some different sizes of raindrops. So when we're talking about a typical raindrop, we're about 2 millimeters. But a large raindrop is up to 5 millimeters, and that's where we're going to get into a falling of about 20 miles an hour, which is why you can hear so well when a large raindrop hits pavement if you're outside or say on a porch and you're uncovered. Plus, some of you have been hit by those, and they have the ability to do a pretty good job of letting you know that you just got hit by a pretty big raindrop. They have a tendency to have a force that can be felt. So here's here's the warm cloud precipitation process. Remember, this is not cold cloud, that is Bergeron. This is our warm cloud precipitation. This would be like our tropical areas. So when we consider what we receive in this region in southern Indiana for our precipitation, is it going to be an entire column of warm air over the top of us, or is it more than likely going to start with snow? Most of the time, it's going to start with snow or crystallization at the top. So those are going to be where we see that communication being met in regards to this cold and warm cloud. Here is a vapor trail of 2014 in February, and one of the things that's unique about this is it does such a nice job showing a pretty impressive storm. Now, although it does say tonight's rain and snow, that's not that connection to this season, but it does show how there is a swirling mechanism that takes place, and we can have that enhancement of water vapor. So satellite water vapor imagery shows how well these pulses of energy can be predicted as they're caught up in the jet stream. So for this particular storm, we have a jet that was moving in this area, and then we have an interaction with the storm, and these impulses here were going to be broken off, and that allowed us in 2014 to have different types of impulse storms, which was pretty active. This was at the kind of the heart of a very active time period, which caused us to have unprecedented snow days for the year of 2014. Quite impressive there. Here we have forms of precipitation. No surprises here. The ones I would really focus on as far as maybe new content is something called rime, very delicate. It's kind of a crystalline form there that takes place at the surface. Hail, you should understand already pretty well. We'll look at a slide there a little bit. Graupel, think of slush in clouds. That might be a bit new there. So those are the two that I would focus on, really maybe learning new information about. It's freezing rain, glaze, we're familiar with that here, but we do have descriptions that are in this column that we should be able to identify within a multiple choice style question sequence or in a open response style. So when we look at the form of rain, cloud burst and drizzle, we have this discussion that we can now bring in about the diameter. So when we're talking about diameters of at least 0.5 or less than 0.5, we're getting into those different types of precipitation. So at least 0.5 is for rain, and then drizzle, we're less than 0.5, and that gives us our difference from that. Virga is something that is rain that doesn't make it to the ground, it evaporates out. So it's a very dry level underneath a cloud that is precipitating. Some of you that have your pilot's license or they're doing your check flights or just working on that you may notice that can be easily seen in the Ohio Valley from time to time. And then the mist contains the smallest droplets there. Forms of precipitation that we've heard of before, snow and then sleet, we've got those, and then freezing rain, sometimes referred to as glaze. They're super cool. These guys are falling. They want to freeze. They just can't yet. And so as soon as they hit anything that is right there at that freezing, it instantly, almost instantly flash freezes as soon as it splashes down, and it makes a donut-like glaze that can be absolutely treacherous. And if it builds up, unfortunately, that causes those pesky outages electrically. And some of you can remember that we had a week or so of outages from several different types of storms in the past. No fun. Here's hail. Hail forms because of updraft. So what we have is updrafting warm air, which is the driver of this. We have graupel. Think slush up here. That graupel is falling, and then it gets pushed back up, and it goes above the freezing line, solidifies, picks up a little mass, falls again. Gravity pulls it back down, pushes back up, way high up there, picks up more, really gets larger, and then finally falls. And if this storm is really aggressive, it's just going to keep processing that over and over again, and we can get some amazing size hailstorms whenever we see those. In our region, what we experience the most is something that would be like nickel-sized hail being most damaging, dime-sized hail, pea-sized hail, quite common. Rime is something where we have a depositing formation of ice crystals. Surface is below freezing, and we can have a supercooled fog, and that's where we have a very crystalline formation that builds outward from that. Kind of a neat form of frost in sense. How do we measure precipitation? Well, we use a rain gauge, something called a tipping bucket. Some of you have not necessarily a tipping bucket, but an electronic rain gauge around your house that tells you how much rain you've gotten at a specific location. We can use those, and they're becoming more and more widely populated. Weighing gauge, we can collect rainfall there. If we're talking about snow, we're going to use a snowboard. Not the one type that you're skiing on, but a snowboard where we can measure depth. And what we have is a uniform depth that can be used typically from a device like a simple ruler, but we need a board that is of certain color, and we want to alleviate that radiation gain from it. So most of the time it's white or at least light colored. Weather radar, we're using radio waves to measure precipitation, and most of you have heard of the term Doppler radar. We will talk about that more specifically in class. That is something that is in process of being upgraded across the nation. Right now we're using a WSR-88D, and some of that is being upgraded to a newer higher definition form of that, and that's been tested out in Norman, Oklahoma. Some pretty impressive storm velocities. And we'll look at the effect of that within the upgrade cycle. Intentional weather modification. Hopefully we'll have time this term to talk about this. Quite intriguing. It borders on the line of environmental sciences, but it definitely has roots and direct connection to meteorology. But there are parts of the planet that are intentionally modifying the weather. And the reason they're doing that is mainly for personal safety. For example, we may not want to experience such large hailstones, so we try to dissipate some of that energy. There might be parts of the planet that are that experience unusual prolonged periods of drought, so we want to try to break those periods up and make the atmosphere precipitate. There might be areas of the planet that are just too hot, and it would be nice during July and August, or whichever hemisphere they're in. Maybe southern hemisphere in December. Maybe we want to shield that radiation and create a radiation shield by producing a cloud cover. So what we've tried to do before is intentionally modify weather. This has been around for quite some time. We've tried to break fog up. We've tried to break storms up. We've tried to make clouds precipitate, and the results are mixed, and that's at best. So what we've learned is it takes a lot of condensation nuclei. It takes a lot of dispersal chemical to get this material to do what it's supposed to do, which is modify the weather. And we're not doing a very good job of it, but we're still trying. In this nation, the state that is doing the most of this now is California, mainly because of drinking water. And they're trying to produce a modified environment in the weather where they can help sustain more drinking water for an area that is becoming increasingly more dry over longer and longer periods of time. So we talked about the hail suppression. Ineffective, we just can't do that. We've used things like silver iodide, think like flares, roadside flares. Sometimes we tried to use ice crystals before that, dry ice, mixed results, really not a good job there. It's just hard for us to get in the atmosphere, and it's even harder for us to take something up into the atmosphere in mass quantities and disperse it effectively to do what the weather does on its own naturally. So these are things that we try to do. Now, the second tier of this slide, several methods of frost prevention. These are things that are preventative measures. So this deals with agricultural pursuits, especially orchards that generate the foods that we like. So think like citrus crops in Florida. Whenever they have a freezing situation, it can knock out an entire crop, an entire year's worth of citrus. And so to prevent that, they can use wind mixing machines. They can fly helicopters in different areas. They can try to use things that are called smudge pots, which are quite dirty machines in the atmosphere. In our region, we have farmers that have much smaller farms that are orchards, and they sometimes have used the burning of tires to produce a changed environment, to produce a thicker atmosphere. We just don't have the larger farms that they do. Agriculturally, you can also use sprinklers to try to produce a glaze of ice over very small would-be fruit, which are typically at the flower stage, at the pre-flower stages, at the budding stage. And believe it or not, that ice coating can be an insulator because the ice will not depress in temperature as quickly nor as low over a one-night stand of unusually cool temperatures. So orchard heaters, they're the most successful. Orchard heaters are not only, as the slide says, the fuel cost can be significant. I mean, it just goes straight up in a lot of situations there, but they're also called smudge pots, like was mentioned, and they are not friendly for the environment. That'll do it for chapter 5. Thanks for tuning in, and keep up the good work. What this chapter focuses on is pretty obvious. A big chunk of this chapter is going to be the clouds, so make sure that you can focus on those well during an assessment, and also make sure that you can discuss The associated precipitation. We have two types of precipitation makers as far as the cold cloud and warm cloud. And then we wrapped up with a modification of the atmosphere that is intentional, and it makes for an interesting discussion as well. Thanks for tuning in. See you in class.